Alright, so our goal is to look at calibration methods for IoT air quality sensors, right. You want to do this, but you may now be wondering why is it being done before you do any system building or any sort of any demonstration is being done. We are already looking at calibration methods. The reason why I am doing this prior to any system building exercise is only because this is a very important topic, number 1, and your electronics sensing system, all that is all fine, but if you do not have a good calibration handle, it is of no use building anything with respect to air quality. That is the second reason. Third reason is this is purely algorithmic, okay. It does not matter whether it is air quality or anything, whether you have data or not. You have to understand the algorithms which go behind calibration, and as I said, these are some of the latest topics in calibration, and particularly applying statistical learning and machine learning techniques has taken the forefront, and therefore doing this as a module to get you a feel for the problem is really not out of the place. However, how good your data comes and how good the statistical learning and other machine learning techniques can be applied will largely be dependent on how good your data is, right. Therefore, before we get into anything with respect to calibration methods, let us understand what are these sensor specifications, okay, mainly specifications of sensors, and I am just going to concentrate on electrochemical at the moment. You can make a bulleted list for the semiconductor sensors as well, okay, electrochemical. One of the first things that you will be looking at is linearity, because this is linearity. See, this is a subject on instrumentation, sensors and instrumentation. There are some very common terms, repeatability, linearity, resolution, accuracy, all these terms are all part, repeatability, all these things come part of any sensor specification. So, linearity is one such specification. First thing that occurs to you is if you have a sensor, you should say what is its linearity, is it a linear sensor, right. So, linearity is an important requirement. So, it best shows linearity in a range. So, you do not define a sensor's linearity over a full range, it is never done that way. You define it over a range and you say between this ppm to that ppm or micrograms per meter cube, depending on how you want to use different units, you define it over a range, right. And I flash to you ambient air quality range, I also flash to you the exhaust, vehicle exhaust range. So, if they are linear in the range of measurement, fantastic, that is all you are interested in, right. So, linearity is best linearity in the range, in the specified range, that is all you are looking for, okay. This is one spec. Second specification is if it is slightly beyond the range, specified range. Now, if it is greater than specified range, what will happen? Will the linearity will be not guaranteed? Yes, that is the point. You can also have a maximum. So, this leads to another spec which is called maximum overload, okay, maximum overload. And so, maximum overload is the linearity not guaranteed, linearity not guaranteed, linearity is not so it is inaccurate, and okay, and therefore also another problem that will happen is if you work in this maximum overload situation, sensor takes a long time to recover. This is important. Supposing it is doing a measurement and because you are going beyond the maximum overhead or overload condition, the sensor will have to recover from that condition. So, the next few measurement results are going to be inaccurate. Whatever is your learning technique, be careful, you should not overwhelm the sensor, you should not go beyond the maximum overload and go beyond the linearity region of the sensor. Supposing it is meant for measuring, let us say typically let us take the ambient measurement. Let us take this chart. Okay. This is the range over which you want to make a, this is not something I keep repeating 100 times repeatedly, this is not the range that is acceptable for human breathing. This is from a sensor's perspective, this is the range over which you want to make a measurement. Sensor takes too long. So, for example, if this is the measurement that you are doing and you suddenly realize that you have passed during testing phase a gas NO2 gas essentially over and above the 200 ppb range which was guaranteed by the sensor, then it is going to get overwhelmed and it is going to take a long time for the sensor to come back and make a proper measurement. Therefore, your calibration methods will work very good provided you take care of the basics of gathering good quality data, proper data by adhering to these requirements. So, maximum overload condition is an absolutely important requirement. Then the other one is sensitivity. The other one is sensitivity. It basically refers to the ppm, parts per million of the target gas. Okay. Target gas, this is pretty straightforward. You look at you have to look at what you want to measure, what is the range over which you want to measure, and also ensure that your sensors are capable of measuring to that value. Then there is something called response time. Okay, there is something called response time. Here it is the response time of the gas sensor. Okay, number 1. It is the response time of the gas sensor. It should take, let us say, typically 90% of whatever the time taken to reach 90% of the applied gas. So, time, so it is a time take, it is about response time, right. So, it is time taken to reach 90% of the target gas concentration, okay, gas concentration, okay, concentration is typical of what is called T90, that is T90 means T90%. So, T90 is what people talk about. You pass 10 ppm of some gas, the time it takes to reach 9 ppm, okay, that not actually to reach, the time it takes to read 9 ppm is what you are looking at, 90% of the target gas concentration. It is a very naive example, but response time is important, it is called T90 response time. So, you should ensure that whatever calibration methods that you are applying, your input data quality is guaranteed and it is doing all these things. Then zero signal, even this becomes crucial when you are training your models using any of the analytical any of the statistical and learning techniques. Okay, there should be no sensor output under clean air. Now you will have to understand what is this clean air. Is clean air at all? Your problem is you do not know what is clean air. Okay, where is your reference, right? That is why they say clean air is also called, I will say it, clean and dry air. Typically people say clean and dry air, clean air or dry air, clean and dry air, I will call it clean and dry air. What is this air? This air is 78.09% of nitrogen, right, and 20.95 of 20 of oxygen, then 0.93% of argon and 0.04% of CO2. Okay. This is what it should be. This is what you are expected to have: clean and dry air. Clean air, this is clean air. This is what you should be breathing all the time, right. So this essentially, I hope this will add up to 100%, and if any change occurs, then essentially the other gases, the partial pressure of other gases will increase, creating uncomfortable feeling for humans. So anything you do is it should not have any other pollutants. Under no pollutant condition, under clean air condition, you should get 0 output. Then there is something called baseline shift. So I have put one arrow here, I will put one other arrow here. There is something called baseline shift. Okay. So this essentially is some sort of small drift, non-deterministic, small and non-deterministic temporal variations, right, when it is exposed to the target gas. Okay, when it is exposed to target gas, that means it just does not indicate that a single value, but keeps drifting up and down a little bit under ideal conditions, target gas, temporal variations even in the presence of the target gas. Okay. It affects the ability to measure the gas accurately. So if it is fluctuating too much, you will have a problem, and so you will have a lot of false alarms. If it is well within the measurable range without too much of variations, small, extremely small, I would say extremely small, it can be non-deterministic, but extremely small temporal variations of in the presence of target gas, no problem, leave it. But if it is too much, you will have too many false alarms, then you have problems of, then maybe the sensor has aged, that means it has come to end of life. Okay, there are some manufacturing defects, and aging and so on. Then perhaps it is having too much of cross sensitivity. Because of its age, it perhaps has developed a lot of cross sensitivity, interfering gases are too much, it has some problems in trying to work under ambient pressure. Okay. And therefore you may have to, the only way out is frequent calibration. So you are back to the same problem. Supposing you want to do if you want to do calibration methods, now your question will be, you also have to account for what is the baseline drift that is coming into the system, so that even that is accounted for, and with ensure that you resolve this problem of baseline shift. Then there is resolution, I will put one more arrow here. Then there is resolution. Well, this definition is quite simple, straightforward, whatever you knew well. Smallest separation essentially, right, smallest separation between two adjacent points, right, and so you should be able to say the gas sensor has a high resolution. alright, and so better resolution not only from sensors perspective but also from the instrument that is displaying the value. So it should also be including that. Alright, so one good thing about electrochemical sensors which I wanted to tell you is that EC sensors have good linearity. One of the major I would say positives of electrochemical, although they have limited shelf life and they have to be frequently replaced, recalibrated and all that, this perhaps is a very strong point. They maintain linearity. However, the electrochemical sensors also suffer from the fact that they require bias voltages. Bias voltages will be required. See, this is one thing about gas sensors and measurements and so on. If you look at if you look at the semiconductor sensors, they have typically initially you have to heat them for something like overnight, okay, and only then you have to start making a measurement. So when you buy it off the pack, you cannot start using it directly. I will pass through the steps for you, and you have to ensure that it is kept overnight and then only then it can actually start making a proper measurement. Now the issue is there is a sensor, the sensor pack will have a heater and there will be a sensor output. So heating is an input, sensing is an output. Now it turns out that you can't make a measurement if the heater is off, okay, the value is not going to whatever you read is going to be incorrect. Therefore if you do any energy power management strategy that you want to do and so on and so forth, that is a bit hard because the heater should be on all the time if you want to do a quick measurement of, let us say, NO2 somewhere you are going in some road or somewhere you want to do exhaust ambient you want to do and you are in front of a traffic signal, you can't keep your the heater off for surely with your semiconductor sensor, the heater has to be on all the time. Maybe sensing can be kept off, kept on, and you can read it. People may actually as electronic engineers, we also know that if you are not able to if you want to save power, you do not need to have a linear power supply which is connected to the heater. You can do switching, right, you can do pulsing, you can pulse and therefore save a lot of energy because you will only be like a DC-DC converter output, you will be just pulsing the power. Now here is the problem that pulsed power is also not acceptable to several of these air quality sensors. Therefore you are forced to keep a linear power supply, you are expected to keep a good DC and keep the heater on all the time. So again do not worry so much about energy consumption, power consumption and so on because this is about betterment of life. You must ensure that this has to be on all the time. So keep these things in mind when you do any system design. So coming back to electrochemical, it is the same issue here. You definitely need a bias voltage, you basically need what is known as a potentiostat function correctly. Most often you will need to work like a potentiostat. So potentiostat, okay, you essentially are talking about a potentiostat. So the biased sensor requires a warm up time of about 6 hours or so, 6 hours of warm up. 6 hours of warm up and then you ensure that it is stable enough and then you start you apply the correct bias voltage. Correct bias voltage has to be applied, you apply the correct bias voltage and then you stabilize the sensor, right, and after that you essentially start using it. So you read the data sheets of whichever sensor that you have shortlisted carefully to know what is the heat up time or the warm up time that is required both in the case of electrochemical as well as in the case of semiconductor sensors. Finally there is another term which you have to note, which is the temperature data. Temperature data. of any sensor, and so temperature dependence on gas output is an important parameter. You may have to do temperature compensation. Compensation of temperature is an important thing, and so you will have to keep a note on that. So I would say, so before you go into any calibration methods, understanding algorithms, think about the kind of sensors that you have with you, and the kind of specifications that you have laid out, so that you collect good quality data and then move on from there in terms of trying to do calibration, right. So this is what I wanted to tell you before even we go into any calibration method. Let us now get into some of the statistical learning techniques for calibration of these IoT sensors. The simplest you can think of is the linear regression, and you can see that in this book. Let me expand it so that in this paper you will see that the linear regression is explained. For each sensor a calibration function was established by assuming the linearity of the sensor responses with reference measurement for each pollutant. Ordinary linear regression was used with the minimization of square residuals of the sensor responses versus reference measurements. The calibration functions were of the type RS is equal to A dot x plus B, where RS represents the sensor responses and X is the corresponding reference measurements of air pollutant. Finally, the measuring function, the converse equation X is equal to RS minus B by A, was applied to all sensor responses in order to predict air pollutant levels. So how do you get to this? If you look up any textbook on linear regression, you will see some simple definitions. I just wanted to quickly capture this. You basically have what is known as a response variable, which is nothing but the estimated variable of interest. In order to get to this estimated variable, you need what are known as predictor variables, and these predicted variables are essentially quantitative by nature. So you could perform several arithmetic operations on them, multiply, add, divide and so on. These are essentially variables used to predict the response. So the response variable comes from the predictor variable, and therefore you use this regression technique to develop these linear and nonlinear models. Okay. Now if you take a single predictor, if you use a single predictor, you essentially call it simple linear regression model, okay, and that is a pretty straightforward I would say definition. And if supposing you want to show, it is very intuitive, X is there, you have Y, and supposing this is your these are your set of points, okay, essentially sensor measurements that you have done, and you have a line like this, or nothing to you have points like this is again X and this is Y, and you have a fit like this, either going down as X increases Y is going down, or the opposite, as X increases Y is also increasing. Both are extremely good regression models. But if you have a crazy system which essentially is like this, now supposing I have X here and Y, you have points like this and you have fit like this, okay, then you have errors, right, a lot of error is there in these points. So essentially your measured value and your estimated values are all incorrect. So therefore you would essentially say that there is a lot of error. Now even here, if how do you sort of quantify this error? This is the problem. How do you know your model is good? Because it is nice to see visually that there is a line fitting and then the points are all close by, and perhaps everything is hunky dory in case A and case B, but in case C, as you know, the error is high. How do you do it mathematically? So you need a metric which talks about these errors. In other words, if you have a positive error, the estimated response is less than the observed response, okay, and while the others are negative. So all those situations are taken care, and ultimately you need a criteria. That criteria typically is the least square criteria, okay. So in the least square criteria, you basically have a mathematical definition for least square, which says y hat is equal to b naught plus b1 times x, okay. Now what is your error? Error is essentially yi minus y hat of this I. This is your error, this is your error, E is error, E is error. Very basic stuff. I am just trying to give you in one go everything, so that you will be able to sort of piece things together. Now when you talk about the best linear model, you look at sum of squares error, okay, sum of squared errors, sorry, sum of squared errors, okay. When you say sum of squared errors, you have to put a sigma of what, of EI, and you have to do a square, and what is I going from 1 to this n complete set of samples. This is what you talk about SSE, right, is equal to sigma I going from 1 to n, you have yi minus b naught plus minus b1 I, not b1, bi, sorry b1, sorry b1 xi, it should be b1 xi, okay, wholes square, okay, and you have the sigma here. So it will take for all the samples, okay. This one should be equal to 0, that means it is the best linear model, and essentially this paper is talking about that only. This paper is saying essentially the same thing. I want you to fit that understanding I showed you with this, so that you exactly know what is it that you are trying to predict, the how you are able to predict the air pollutant levels. Alright, so you have multivariate linear regression, that is another way of calibration was carried out using linear square method, and you have, like LR, the calibration functions consisted of equations of types RS is equal to function of x comma yi, and is a function of multiple reference measurements, and then you have some numbers coming up. So let me quickly move on to this part, and it is applied to each sensor, and so that is another way of another technique for calibration. Then you have the third technique, which is the artificial neural network technique. These are quite sophisticated modeling techniques, and you can see that able to model extremely complex functions, and you essentially talk about radial basis functions and functions and multilayer perceptrons, essentially MLP as they are called. The radial based functions are not so good, it seems, from this paper study, and it appears that MLP, multilayer perceptrons, seem to work very well, and The most popular architecture used today due to original people who invented this architectural system seem to give good performance results. So, essentially you are talk about a number of inputs either from original data or from output of other units in the neural network, and you will have typically one hidden layer with several hidden units, and then the weighted sum of inputs is formed to compose the activation of the unit, and with a number of defined layers and a number of units in each layer, the network's weights and thresholds must be set in order to minimize the prediction error made by the network. So, you use for training algorithms such as back propagation, which is typically an algorithm called BFGS. You can see here Broyden, Fletcher, Goldfarb, Shano algorithm. The most recommended techniques are all mentioned in another reference paper, and to automatically adjust the weights and thresholds in order to minimize this error. So, essentially you are trying to again get back the closest value measured value, the measured value should be closest to what is the actual ppm value measured off by the sensor in its linear region. So, all the objectives is essentially that you should be able to apply either statistical or this machine learning techniques in order to arrive at it. So, this paper if you read this paper you will get some idea on how one can apply these little techniques, and there is not much scope for us to spend more time than this, but you can see that there are predicted sensor values which are shown here in these results, and they are trying to estimate as close as possible, and they are trying to calibrate the sensor, right, because if you read a voltage you should know from that voltage what exactly is the ppm ppb levels, and only then you know for sure that your calibration is good. So, I urge you to read this paper in detail, and also to highlight to you that it is a very important technique for you to make a measurement. So, one thing that occurs is that measurement uncertainty estimated by orthogonal regressions of sensor outputs versus reference data, ANN appears to be very good, because LR and MLR have shown to produce highest measurement uncertainty. So, therefore, moving in the direction of artificial neural networks to calibrate sensors perhaps is a good positive way to move on with air quality measurements. And also this problem of cross sensitivity is an issue which is a problem for several sensors, and therefore it is good for you to also check that the ANN techniques can also solve this problem of cross sensitivity. So, I would say that it is a very important piece of paper, that piece of work that you may want to ultimately understand and sort of use it in all your future endeavors for calibration of sensors.